do an example now applying the properties of the confidence interval to actually calculate a confidence interval for a proportion. So let's say that we have a planning committee and they need to estimate the percent of students at a large university who will attend an upcoming event so they can determine an appropriate location. 80 students are randomly selected and 15 say that they will come to the event. What is a 95% confidence interval for the proportion of all the university students who will attend? Interpret the interval, and also we want to know, is the confidence interval a valid method for this problem? Okay, so the situation is we're interested in the proportion of all students who will come to the event, but we only have a sample of information. We just have these 80 students. So let's write down some key information. We have a sample size of 80. And we were told that of these 80, only 15 will come to the event. So let's figure out our proportion of the sample that will come to the event. So that is 15 out of 80 are coming from the sample. That's about 18.75%. And a couple of the properties that I want to check is I want to know, am I working with a sampling distribution that's approximately bell-shaped? And the way I'm going to check that is I'm going to check, is n times p hat at least 15? And is n times 1 minus p hat at least 15? Question mark. So I'm going to say, is 80 times 0.1875 at least 15? That is actually equal to 15. So that checks out. And then I have 80 times 1 minus 0.1875. And that is equal to 65. And so that checks out. The other property that I want to check is, do I have a random sample? So I'm going to abbreviate that RS for random sample. And I do. So that checks out. And so I will just make a note here that the confidence interval is a valid method because 1, I have a random sample that was given in the problem, and 2, I have n times p hat and n times 1 minus p hat are both greater than or equal to 15. All right, the whole concept of the confidence interval is based on the idea that the distribution of sample proportions is bell-shaped, and so that's why I need this piece. That piece tells me that we're working with a bell-shaped distribution, and the random sample gives me an unbiased estimator. All right, if I chose the sample in any way that wasn't a random sample, then I might end up with a biased point estimator. Okay, so now we're ready to calculate the confidence interval. And so I'm going to say I need p hat plus or minus a z-score times p hat times 1 minus p hat all over n. All right, and so that's just the formula that we saw previously for the sampling, for the confidence interval for a proportion. And so we're just going to plug in values now. P hat was 0.1875 plus or minus a z-score. And to find that z-score, you're going to always just use these values in the table. You can just get to where you have those memorized. You use 1.96 for a 95% confidence interval, 1.645 for a 90% confidence interval, 2.58 for a 99% confidence interval. Those are going to always be the same when you're in the proportion setting. So this is 1.96 for Z times 0.1875, 1 minus 0.1875. This whole thing is over n, that's the total sample size, which is 80. So this turns out to be 0.1875 plus or minus 1.96 times 0.044. Right, and then that simplifies to 0.1875 plus or minus 0.086. And now I'm just going to add 0.086 to 0.1875, and I get an upper limit of 0.274. When I subtract, I get a lower limit of 0.102. All right, let's just make a note that this piece, the 0.044, is the standard error. Once I multiply that point times 1.96, I get 0.086. That is the margin of error. I'm going to abbreviate that MOE. You'll see that a lot. That is for margin of error. Okay, and so now all I'm going to do is I'm going to go ahead and find a 90% confidence interval. And so the only thing that's going to change is my z-score. So instead of using 1.96 for the z-score, when I do the 90% confidence interval, I'm going to look back at that table, and I just need 1.645. So let me go ahead and write this out. I'd have 0.1875 plus or minus 1.645, and then I'm just going to multiply it by the standard error, which we found was 0.044. And this works out to be 0.12, and the upper limit works out to be 0.26. Now for the 99% confidence interval, again, all I'm going to change is the z-score. I have to add and subtract 2.58 standard deviations. So that gives me a lower limit of 0.07 and upper limit of 0.30. I'm going to plot those three intervals on the scale so we can see a pattern. For the 90% confidence interval, let's start with that one. That's our lowest level of confidence. We went from about 0.12, which is about right here, to 0.26, which is about right here. For the 95% confidence interval, we went from 0.102 to 0.274. So from about right here, at about 0.10 over to 0.27. So somewhere in here. And then for the 95th% confidence interval, I went from 0.07, which is about right here, to 0.30. And what I want you to notice about this is that when I moved from 90 to 95% confident, that was from here to here and here to here, notice that the width of the interval changed, but it did not change as drastically as when I went from 95 to 99%. Okay, so notice that this is a, notice that moving from 95% to 99% increases the width of the interval. More so than 90% to 95%. All right, and let's just think about why that is. Well, when you have the bell-shaped distribution, when you get out here in the tail, to get out to 90%, you have to move further along in the tail to get more area. So once these tails start getting skinnier, you have to move further and further out to achieve that 99% confidence interval. So you can see that even in the z-scores. 90% of the distribution is within 1.6 standard deviations of the mean. 95% is within 1.96. But to get to where we have 99% of the distribution, we have to move out even further, 2.58 standard deviations. And again, that's because these tails get so skinny out here in the extreme. So that's just a pattern to be aware of. All right, now we have not written an interpretation for our confidence interval, so we want to think about that now. How would we write a good interpretation of our confidence interval? Okay, so actually I'm going to start by writing a good interpretation. So just thinking back to the 95% confidence interval, we could have written, we would say something like this. With 95% confidence, (10% to 27% of all students will attend the event. Okay, so a couple things that need to be present in the interval interpretation to make it a good interpretation. We need to make sure that we're inferring out to the whole population. The whole purpose of the confidence interval is that we took a sample proportion and used it to infer out to the whole population of interest, so all students at the university. Also, you want to put it in context. You don't want to just say the confidence interval is 10 to 27%. So put it in the context of the problem that we're talking about. So let's take a look at some bad examples. So this would be a good interpretation. All right, and just note that these are all bad interpretations that I'm about to show you. All right, so in this first bullet, it says we are 95% confident that between 10% and 27% of the sample will attend the event. So what is, why is that not a good interpretation? The statement should be about the population, not the sample. I don't need an interval for the sample. Okay, I know the percent of the sample that's going to attend. We found that up here at the top. It was 0.1875. Okay, so the statement is about the population, not the sample. We don't construct confidence intervals for sample proportions. So this is the issue right here. The next statement, it says the 95 confidence interval is from 10% to 27%. Mathematically, it's correct, but we want it to be in context, not in context. And then the third one says, for these 80 students, between 10% and 20% will attend the event with 95% confidence. This has the same issue as the first one. It's making a statement about the sample and not the population, and that is what the issue is there. So make sure when you're asked to write an interpretation, you write a good interpretation and that you make it clear that we're inferring out to the entire population of interest.